Alrighty, welcome to day 13, everyone. Lucky number 13. Let's see what this has in store for us. I haven't reset this to use day 13 yet. Let me do that now, as the puzzle should be coming out right about now. Let's see, what do we got? You climb the hill and again try contacting the elves. However, you instead receive a signal you weren't expecting, a distress signal. Your handheld device must still not be working properly. Packets from the distress signal got coded out of order. You need to reorder the list of received packets to decode the message. Your list consists of pairs of packets. Pairs are separated by a blank line. You need to identify how many pairs of packets are in the right order. For example, packet data consists of list of integers. Can't read today. Each list starts with a bracket and ends with the brackets. That contains 0 or more comma separated values. When comparing two values, the first value is the left and the second value is called the right. Then, if both values are integers, the lower integer should come first. If the left integer is lower than the right, the inputs are in the right order. If the left integer is higher than the right integer, the inputs are in the wrong order. Otherwise, the inputs are the same integer. Continue checking for the next part of the input. If both values are lists, compare the first value of each list, then the second value, and so on. If the left list runs out of items first, the inputs are in the right order. If the right list runs out of items first, they're in the wrong order. List same length, no comparison decision needed about the order. Continue checking. If exactly one value is an integer, convert the integer to a list which contains that integer and it's only one value. Then we'll try the comparison. For example, convert the right to 2 results and then find compare. Okay. Using these rules, you can determine which of the pairs of the example are in the right order. Left side is smaller, so in the right order. Right order. Okay. What's the sum of the indices of? Okay, so what are the indices of the pairs that are in the? What are the indices of the pairs that are already in the right order? The first pair is index of 1, the second pair, okay. Okay. The pairs are in the right order, so 1, 2, 4, and 6. The sum of these indices is 13. What are the indices of the pairs that are already in the right order? Why is it 1, 2, 4, and 6? Wait, what are the first pair has an index of 1, the second pair has an index of 2, and so on. The example of the pairs in the right order are 1, 2, 4, and 6. Okay, pairs as in, I gotcha. The sum of those indices, gotcha. Okay, well, this is gonna be fun. Parsing this is actually not a problem. It's not hard to parse these. The problem comes with actually solving for that parsing. So what we're gonna do is we're gonna do for int I equals 0 while I is less than inputs dot size, and then we're going to do I plus equals 3 because there's 1, 2, and 3 are on 1. So we have to compare these. Yeah. Can we just read left to right? Is that a thing? We get a list. What are the orders? So if both values are integers, so if both values are lists, compare the first value of each list, then the second value, and so on to the left. If both values are lists, compare the first value of each list. Okay. I think I understand this. So what we need to do, we're gonna basically just do recursion. So we're gonna do private void and compare. We're just be comparing two strings. Actually, what's gonna be happening. And string S1 and string S2. Because is it the best way to compare the strings, or just to, is it to break it all down? You know what? Let's parse this out. Let's parse a line. So public or private. Let's make a class. I don't know why I put that there. Public. Let's do this kind of the more object-oriented way. Static class, and this is going to be a. I don't want to call it a list, but call it a comp list. And so they have to be a comp list, right? I think everything is a comp list to start. Right. Private, we're gonna need like a common node, because it can be a comp list or it can be a like an integer. Static class. This is going to be a comp node. So list is going to have a list of comp nodes. And this is going to extend comp node. And so we're going to get a public static class. This is going to be a comp number. Extends comp node. And this one's just going to have integer value. No. Int public. There we go. Okay, so there's our list. So now we just have to basically parse this out. So we have to build up these comp nodes from this. So what we can do here is we're going to need a private node, not node, comp node. And this is going to be a parse. Let's call it a parse method. String S. So this is easy because it's gonna be public void and parse, or public static comp node parse. So this is easy because it's gonna be a number and we're just reading till we have to get to a comma or an ending bracket. So is it better to have this be a list of characters? Now let's just keep it as a string. And we'll have an index here that we're kind of using. So for this one's easy because all we're doing is we're returning new make constructor int value. This dot value equals value. New comp number. And so we're just going to do is string int. This is going to be comma is s dot index of a comma starting at index. Is there any spaces? No. Good. That makes life easier. So there's the comma, and here is going to be the square brackets. One of these has to end it. And so what we're just going to do is string num is going to equal s dot substring from index to math dot min of comma and square bracket, which is uppercase S for some reason. And then this doesn't need to be in here. Actually, this works better if it's not in here. So we're gonna put this in the parse set. So what we're gonna do is we're gonna have an int index equals 0. While the index is less than s dot length. Do this. Char c is going to be equal to the s dot char at index. If c equals an opening bracket, that's going to be one thing. And I don't think there's any other reason. I think it's either an opening bracket or it's going to be a number. I don't think we have to worry about any other things. Okay, so what we're going to need to do is we're going to have a comp list, because the list is always going to start it. And we're going to return the comp list. Equals null. We're going to have a special case here. Is if index equals 0, comp list, list equals new comp list. And this is going to be a special case where we're setting comp list equal to list here, because that's never a problem for this one. Okay. And then here, what we're going to have to do is we need the current, we need to be holding the current comp node. Well, I guess if it's a number, a list has to go through numbers. So we're going to need the current list, I guess. And so we're going to have to do current list dot nodes dot add new comp number. Okay. And it's going to be integer, whoops, integer parseint of this. There we go. Okay, so that will take care of parsing this. Now we get into parsing the node itself. Or actually, well, first we have to do is actually we have to increase int. We have to do index. I guess I should store this string num string. I need this for calculating the length of how far index moves. Index plus equals num string dot length. Okay, so that will increase index there. We need to now parse the harder one, which is going to be the array. So parse gives us a comp node. So this will need an index here. Parsing this in a, well, no, there's one more case. We do need to check if C is a comma, because if it is, we just skip over it. I'm like forgetting how recursive parsing works. This is not how recursive parsing works. Maybe I should have pawned these off. Because this should realistically live inside of here. Maybe I should have pawned this off. Public What if I have another class, public static class parser? In theory, I should have a parser class that has this index stuff in it. This should technically control this. And so we do public void public comp list parse. This should take in a parser, and then that's it. It's just take in the parser. So if we're parsing this, so the first thing you do is technically you assert that that you were asserting. So I'm not gonna worry about asserting that this character is here. I'm gonna assume that my parser is correct. So that is indexed currently. So now we have to do is, first thing you do is you do parser.index plus plus. Let's turn null for right now. This is gonna be a stack, by the way. So what's actually gonna happen is we're gonna be doing comp list is gonna be equal comp list dot parse. So we're going to need a parser equals new parser dot s equals s. Don't need that there. Parser dot index equals 0. Technically that. So that index, that is case, parse, give it the parser. Boolean first. I need to save this beforehand. Okay, so that will take care of parsing a list out. So now we have to take this back, create our parser back in here, public static comp number, parse, take in a parser. Now this will have everything we need. Okay, and we just want to return this, but first we need to make sure we do parser.index, increment it, and there we go. All right, so that's easy. So because we know it's a thing, we actually don't need this. We can cheat the system a bit. Input.get I. We can cheat the system a bit because we know it's always gonna be a comp list first. We can actually just do that. And now we don't need this little method thing anymore. Okay, so now we're on the comp list. Now we just need to parse this out. So we need to check if parser char c is going to be equal to parser.s.char at parser.index. While c does not equal the closing brace, so while we are not at the closing brace for this parser or for this list, we want to keep going. So now we need to do is c equal to a comma. If it is, that's all we gotta do. Otherwise, if it is a list, we comma comp list parse, pass our parser in. Right, it's reading this. Right. Parse, and then we can do, well, we can actually just do straight up nodes add to it. Okay. And then we make sure we do parser plus plus here at the end. Comp list equals new comp list. Sorry, list.nodes and return list. So now that means all we're missing now is else. The only thing left is to parse a comp number. I think that is all we need to parse this out. Ugh. I'm hoping so. Okay. So now we have a list. Can I don't want to like pre-print this, so we're just going to do this. I create a constructor, generate constructor, because this is annoying to not do it without a constructor. And 0. Okay, so we have a list 1 and a list 2. Doesn't matter, we can just redo the parser plus 1. There's not really a way. I mean, it could add some 2 strings, but this is fine for right now. Cool. So this generates a line, and what we need to do now is run some logic on these. So now we need to do the whole comparison, which is this, which is actually now taking a comp list, in. So what that means is we go back to this logic here. So comparing 2 values, the first value is the left, and the second value is called the right. So comparing those, so when we compare 2 lists, if they are both lists, is the first thing, right? Or if they're both integers. So let's start there. These actually aren't comp lists, this should be comp nodes, by the way. So if n1, n2, if n1 instance of comp number and n2 instance of comp number, then we have this logic. Else if it is a comp list is that, otherwise is this. Actually, otherwise we need to do separate else checks. Okay. There we go. So now here's our 4 cases. First case is they're both values. The lower integer should come first. So if this can't be, let's go num1, num2. So if num1 dot value, the lower integer should come first. So does it matter if we're lower than or equal to? Oops, unplugged my headphones. Not that I really need my headphones plugged in. Yeah, okay, so equal. So this needs to return a Boolean. So return that. And we will only, that has to all be true as one is false. Okay, so they're all ands. If they're both lists, compare the first value of each list, then the second value, and so on. Okay. If the left list runs out of items first, the inputs are in the right order. If the right list runs out of items first, then the inputs are not in the right order. So first things first is if this needs to be L1, L2. So first things first is L1 dot nodes dot size is less than or equal to L2.nodes.size, because if it's not, then the whole thing is pointless and we can return false. Otherwise, for int I equals 0, while I is less than L1.nodes.size, I plus. We need boolean valid equals true. And so now we're just going to do valid equals valid and compare, lowercase, compare L1.nodes.get I and L2.nodes.get I. And then we can return valid. If exactly one value is an integer, convert the integer to a list which contains that integer as its only value. Then retry the comparison, for example, k. So if n1 is a number, then we have to do is return. All we do is comp list equals new comp list dot nodes dot add num1. And so now we return compare list and n2. Otherwise, same thing here, but instead we are doing n2 here, and now it's n1 and list. And in theory, sorry, and in theory now, we want to compare on these two, compare list 1, list 2, and if it returns true, we need the index, which is going to be I divided by 3. And we just sum it up. And then we just do a nice good old lap of sum. What are the odds that this is right and has no errors? I'll say, well, I'm almost around. Because it's -1. Math dot max no, math dot, no, it can't be, if it's -1, I guess we can just do this, comma, s dots, parser dot s dot length, comma, oops, that works. It's not pretty, but it works. There's some sort of math, max, min, I'm sure you can do on this to make it work, but whatever. Index 0. Length 0. Oh, sorry. That was backwards. 259. What are the odds that I'm not right? What's their example again? Let's run through their example. What should I be getting? I should be getting 13. I get 8. Okay. System out, print line I. 3. What indexes I'm getting? Oh, I swear I'm off by 1. 1, 4, 6. Oh, 2 didn't work. Yeah, but my indexes are off by 1 because, you know, they start counting a 1. So 2. What's up with 2? Why is 2 invalid? All right, let's see. Skip the first one. I is 3. So let's compare. So wait, it's a list. So I have node and node. First one then is a node, size of 1, value of 1, right? Node 3, 2, 3, 4. Correct. 1 and 4. Okay. So why is this failing? What fails here? Valid, false. Oh. Oh, I messed that. Okay, hold on. I messed that up. Let's get back to here. Okay. So this one was true. And I believe this one was false. So if we go inside of it, 1 is less than or equal to true. Oh, is it maybe this one? Size of 3, size of 1. What's it's comparing? Comparing 2, 3, 4 to 4. Did I do that wrong? The lower integer should come first. All right, sorry, both lists. Compare the first value of each list, then the second value, so on. If the left list runs out of items first, the inputs are in the right order, which it doesn't. Or am I thinking about this wrong? It's as soon as you make the first comparison. The first comparison is all that matters. So that goes away. Of L1.nodes.size. Wait, okay, 2 to 2. The size is greater than I. Sorry, no, if the size is less than or equal to I, return false. Is this gonna fix it? I just get 146. Technically I should be doing that. No, I don't care about the less than bit. Cause so what I do need to do is this compare is wrong. I need go away, Microbytes. This needs to return an integer. What needs to happen? So for number input, so zeros means keeps going. If we get anything besides a 0, that means we're done. So for number inputs, the lower value should come first, which means we want a positive value here. Okay. This returns a -1. Get rid of valid. If compare does not equal 0, return int val. Okay, I see how this is sort of weird. If val does not equal 0, return val. As long as they're the same, that's all we care about. So let's return 0. If all this goes through, then it returns 0. Return compare. Return compare. So only if we get a 1 back is all we care about here. Did I do this right? Nope. Oh wait, greater than 0. We got 1 and 2. Okay, it's a start. It's a start. Four. If the left side runs out first. So this actually is a return 1, not a 0. Return L1.nodes.size is less than L2.nodes.size. Return 1, otherwise return 0. Is that what I'm missing? Hey, all right, let's test with my input now. Please work. That's a lot higher than what I got the first time. Hey, we got it right. Beautiful. Okay, next you need to put all of the packets in the right order. Disregard the blank lines in your list of received packets. The distress signal protocol also requires that you include 2 additional divider packets. Using the same rules as above, organize all the packets, the one in your list of received packets, as well as the 2 divider packets into the correct order. For example, the result of the putting the packets in order. So I'm just doing a giant sort. Wait, I literally just made a giant sort, and I did it correctly because I just made a giant compare method. Wait a minute, can I just sort these? Hold on. List, I swear, comp node, nodes. I'm gonna be really happy if I just did this correctly. I correctly predict this second part. Comp nodes dot add list 1. Add list 2. There's our lap, and then nodes. We have to add divider packets, which is this. I don't want to. I could throw this to the parser, but comp list dot parse new parser. I'll just throw them through the parser. I'm lazy. 2 and 6. And now guess what? Nodes sort. Actually, I think we just do compare. This dot compare. And guess what? Afterward, locate the divider packets and find the decoder key for this intersection. You need to determine the indices of the 2 divider packets and multiply them together. The first packet is at index 1, second packet is at index 2, and so on. This example, this divider 10th and 14th is 140. So multiply them 2 together. Okay, so actually we need to store these. So we need to do comp node div 2. Oops. Use this. Luckily, I can get away with this because they're going to be the same. The objects aren't going to change. So I can get away with sorting these, and I can just straight up find these. In theory, I should have done this correctly, and then we're going to do for comp node in nodes. Oops. Int I equals 0 while I is less than nodes dot size I plus plus. Is it starting at 0? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Nope. Nodes get I. Oops. If comp node is equal to div 2, div 2 index equals I plus 1. Do the same check for 6. And then we just do a lap. I delete the wrong thing. On div 2 index times div 6 index. Don't give me an error. Give me an answer. I got an answer. Oh, but it's not right. So unfortunate. I was literally about to be so happy if that just straight up worked. Okay. What do I get here? 13, I get 45. What do I print div 2, div 6 index? Sure. I'll do it this way. Nine and 5. I'm off by ones. Wait, how am I off by ones? Oh, no, I'm not. Okay, never mind. It's 10 and 14. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's upside down. Are you kidding me? What's the arrays.reverse? There's like a, there's a way to do this. List. Is there no arrays? There's like a reverse method. Stream nodes dot sort nodes dot stream okay, hold on. Java reverse array. There's a built-in method for this. I know there is. Is there not a straight up collections? Dude, Java is like the most. Who decides this, dude? Java is just it's something. It's something. Collections. Okay, there's our answer. Now we're correct. Now we go back to our input, get the right value. Now they're in the right order. Submit it, and there we go. All right. Okay. Dude, sometimes Java just makes no sense. Anyways, there we go. I don't think there's anything for me to, like, literally this is, it's not the perfect code, but honestly, all we did was we built our own compare method and built our own parser. I don't think I could have done this any better, honestly. Obviously, I could have done it faster. I mean, I don't even know what I got. Oops. 2K. It's not that bad, but you know. Anyways, let's go over today's puzzle and how we solved it. So for today, we are given this inputs of, well, they call them just packets. We're just given this input of a bunch of packets. These packets are lists, and they have lists have either a list inside of them or a number. It's really all you need to know is that they're a list and they have list or number inside of them. It just keeps going on like that. So to parse this out, we do, I think this is technically tokenizing. This is like a very simple tokenizer is what this is technically. But we make this little parser class that just holds our string we're currently going over and the index we are currently at in the string and parsing. And the first thing we do is we just simply go to the list. So we know, given our inputs, we know we're always starting the list. We have this little comp node here, which is just kind of this wrapper. That way we can have a list and number be kind of work mesh together in Java. It's just a little hack. It's nothing to worry about. But we know that given our input, we always start with a list. So we simply create a list and we tell it to parse itself. Now we always increase our index by 1 because we know the first character in a list is always going to be this bracket here. So that's why we always increment our index first. Then we grab the next char and we start our while loop that will keep running as long as we don't reach the square bracket that ends this loop. Now you might say, okay, hey, what happens if we get, say we're parsing this one, won't this square bracket here kind of end our loop early? No, because what we'll do is every time we loop through it, we will first check for a comma. We don't care about the commas, so we just skip over them. That's all this is doing. But the second step is checking if we have found another square opening bracket. If we do, we know we found another list, which we will then send it off to and parse it again. So this recursively calls itself to parse it. It'll do the exact same thing we just did. It'll start here and parse it through the list. This helps because, hey, now we're parsing this smaller list here. This will finish, so parse itself and finish, and now we're on to this comma. So no, this square bracket will not end our while loop early because it is being handled by the recursive call. And then our last check is everything else is going to be a number. These are the only characters we have. So then we go ahead and we tell it to parse a comp number, which is pretty easy. We just get the comma or square bracket. So basically we find the next non-number character and we just parse a substring on that. Increase our index by the number we found. These are all 1, so technically I did a little bit excess. Now I guess there's 10, so we could have a 2-digit number. But we increase our index by the length of this number, and then we create a number value that has the number stored. and then return back, and now we continue on our while loops. Now this is skipped over the number. Now the next bit, which is actually gonna be like a comma. Let's say a comma here, that'll parse the number, sees the ending bracket. Now we have ended parsing this inner list. It'll then exit out of this, it'll jump up in the recursive bit, it'll find another ending bracket, so it'll end this list here, it'll then jump up in the recursive stack again, find a comma, skip it, and then so on and so forth, continuing on the parsing. Again, this is a very basic tokenizer. If you've ever done tokenizing, if you haven't, well, congratulations. By doing this problem, you've built a very basic tokenizer. And then from that, that's it. We then call our compare method, which will then compare these two nodes. And all we do is we just follow the rules that are given by the question. Now, originally I did a true or false, but that doesn't work with this compare. Because you go until you find the first right or wrong thing. Being equal is not right or wrong. So you need three state essentially. You need to have a state if it's wrong, a state if it's right, and then a state if it's neither at the moment. And you're still searching for the ending state. So that's why we're using a number on the return for this compare. And so I just used it to be 0 is continue on, 0 means there's no state assigned. A positive number means that we have found a valid solution or a valid compare. A negative number means we have found an invalid compare. And so you can see here's the individual steps. Here is if we have two numbers that we're comparing together, we simply just return the second number minus the first number. This will make it so if this number is larger than the first, it returns a positive number, which is what we want. If this is smaller than this one, it returns a negative number, which again is what we want because that's invalid. But if they're the same, it'll return 0, which will continue on our compare recursion. The second one here is comparing two lists together. This just goes through and it'll compare each individual index in each list. It'll return a -1 if we reach the end of the second list before the first. Otherwise, if we reach the end, if they are the same size, we will return 0 because the same size does not mean anything. But if the first list is smaller than the second list, that is what we want, so we return a 1. And then again, the last two are just if we have one that's non-number and one that is a number, one that's a list, we simply make the one that's a number into a list and then compare it from there. And that is it. That's the compare, and that is how we do part 1. Part 1 again, then we just do find the indexes of the ones that are valid, and then sum them together. Part 2. We've already built a compare method. It just wants us to sort them. So why not just throw our compare method into a sort of our list? And of course, it gives us these two, what I call them, I think I call them like break or divider packets. Yeah, divider packets. We simply just create these two divider packets, throw it through our parser that parses it out in the tree we need, throw them in the nodes list, and then we just sort, passing in our comparison that we just made for part 1. Just happened to work out very well. And of course, for some reason, this separates or this sorts it backwards. It's Java, and so we have to do this nice reverse. But then we just go and find our divider packets, multiply their indexes together, and that's it. That's day 13 done. Hope you guys enjoyed. I'll see you guys out tomorrow for day 14. Peace out.